everyone, welcome back to another topical revision video for CIE A Level Physics. Today we're going to talk about the last important concept in gravitational fields, which is gravitational potential, potential energy, and other related concepts such as escape speed, energy exchange, and most importantly the graphs. So let's start with the gravitational potential. So this is one of the most important and very frequently examined concepts. So the definition for this, you can write it in different ways, but exam-friendly definition is the work done per unit mass by gravitational field in bringing a mass from infinity to a point in the field. Okay, so before I explain this, let me draw a little bit of picture how we want it to visualize this. So for example, let's say this is the mass, point mass, source of the field, and we already know that this field looks like radial. Okay, so field lines are radial, we already know this. So this means that when we are trying to bring a small test mass, actually you could write over here, bring a test mass. This is our test mass at infinity, and we want to bring it somewhere over here. Let's say for example at some distance r from the source mass. So since we know that the gravitational force is this way, so the gravitational force is this way, so this would mean that when we say work done by gravitational fields, it is positive towards that source mass. So to bring it from infinity to a certain point, that is the gravitational potential. So certain key things that we need to remember: that work done by gravitational field is positive in direction of the field. Okay? Towards the mass. But work done against the gravitational fields, work done against gravitational field is positive opposite to the direction of the field, meaning away from the mass. So this difference you have to remember. So when we say work done by gravitational field or gravitational force in bringing a test mass from infinity to that point in that field, we're talking about this particular scenario. Since the force is a function of the distance from the source mass, We can't just simply multiply with the displacement to get the work done. So what we can do, we can integrate the force from infinity to a certain point in the field. So basically we are integrating m over r squared from infinity to a point r and dr. So we know that this is like reciprocal of a square. So when we integrate this, this becomes minus m over r from infinity to a point r. If we take m test mass to be a unit mass, we can actually drop this. Now when we plug in the limits, you have minus gm over r minus gm over infinity. This cancels out because this becomes 0, and what we are left with is minus gm over r. And this is our work done, or gravitational potential. Potential 5. So this is the formula for this. Unit for this, since we said that this is work done per unit mass, this is joules per kg. And since this is a form of work done, energy transfer, so it's a scalar quantity. An important concept which we saw over here also, that the potential at infinity becomes 0. This actually is a very important point in understanding why the gravitational potential is a negative quantity. So this is a very important question, a very frequently examined question in fact, that why is gravitational potential a negative quantity? So, first point is that the potential at infinity is defined to be 0. Okay, so this is the limit for this. The following point for this can be written in two different forms. One way to write this, the following point, is that the work is done by gravity in bringing a mass closer to another mass, reducing the potential from 0 at infinity to a negative potential at a point closer to the mass, source mass you could say. The other way you could rewrite the second point is that the work done against gravitational field in separating masses to infinity increases the potential, the gravitational potential, to 0 at infinity. So therefore, at finite distances, gravitational potential is negative. Okay, so at infinity it's 0, so at finite distances the gravitational potential is negative. So these 2 points are alternate to each other. They convey the same thing. So if you prefer the wording work done by gravity, it's reducing the potential again as it means potential to do work, reducing the potential from 0 at infinity to a negative potential at a point closer to the source mass. But if you prefer work done against gravitational field and separating masses to infinity increases the gravitational potential to 0, you could also say work done against gravity in separating or moving a mass to infinity increases the gravitational potential to 0 at infinity. Therefore, at finite distances, gravitational potential is negative. So this is a very important point, question to remember. Now, we need to be able to draw the graph for this. Graph of phi versus r, potential versus distance basically. So since this is a negative quantity, first we are going to write for a point mass, let's say. For a point mass. So this, For a point mass, this basically goes like this. As distance from the source mass increases, gravitational potential rises to a 0 value. So this is your phi joules per kg, and this is your distance in meters. Okay. This also illuminates a few things for us, namely the potential difference. Okay, so potential difference between 2 points. So let's say, for example, this is point, let's say R1 over here, and this is point R2, where R2 is greater than R1. So if we want to find out the potential difference between them, if an object is moving from R1 to R2, from R1 to R2, a small test mass is moved against gravitational field. So we need to figure out how much potential difference there is, right? So what we will do, difference in potential would be potential at R2 minus potential at R1. Final minus initial, right? So you have, minus Gm over R2 minus Gm over R1. So basically what you get over here, this would become positive, Gm over R1 minus Gm over R2. Now, interestingly, if you know a little bit math about the inequalities, if R2 is greater than R1, this implies that the reciprocal of them is the other way around. So R1, so if you multiply the Gm on both sides, you get Gm, and just rearrange, so Gm over R1 is greater than Gm over R2. So it tells us that it definitely has a lower value, right, at R1, okay, but since there is a difference in potential, there is work to be done. This also means that the work done to move from R1 to R2, that means from a point closer to the mass to farther away, you need to increase the potential, and that means we need to apply work against the field. Okay? And to bring the mass from R2 to R1, we are reducing the potential to a more negative value. This means that the work done is by the field. That means work done by the field should be positive. Work done against the field would be negative in that same sense. Furthermore, work can only be done if there is a potential difference between 2 points in a field. Okay, that is a given. So if there is no difference between them, there is no work to be done, either against field or by the field. So work can only be done. Work is done by the field or against the field only if potential difference exists between 2 points in a field. And that brings us to the concept about the equipotential surfaces. So equipotential lines or surfaces, since this is like gravitational field is radial and like radial in all directions, 3 dimensions, so equipotential surface basically. We can say that the surface where all the points on it have the has the same gravitational potential is known as equipotential surface. Alright, so how does it look like? So for example, you have a point mass as before. So equipotential surface would be, that means that you have a point at equal distances or a distance equal distances from the center of the mass. So for example, these lines, when they represent equal distances away from the mass. So for example, this is R1. This entire circle represents, or in fact sphere would represent, an equipotential surface where the potential is the same. So if an object wants to move from over here to over here, so there is no work done required for that. So there is no work done against the field or by the field if the object is simply moving from one point to another on the equipotential surface. Okay. However, to go from R1 to, let's say for example, R2, then you need the potential difference or work done. So for example, if an object moves from over here to over here, then the work is done against the field, because we know that the work, like the force, is towards that center of the mass, point mass, sorry. So work is done against the field. And again, once again, it is only required if there is some potential differences between 2 points in a field. If there is no difference between 2 points on a field, there is no requirement for the work done. Okay. Now, interestingly, gravitational potential is related to gravitational field strength. So let's see what the relationship is between gravitational field and potential. So gravitational potential and field. Alright, so the following differentiation is not part of it, but it helps to understand what we're actually doing. So we said that when we integrate the gravitational force, or let's say force per unit mass, even if you do that, remember we did the gm over r squared, so basically that is the force per unit mass. So if you do the integration of g with dr, you will get potential, right? But when we do the reverse of this, d phi over dr, we get a different quantity, slightly different quantity, but it depends on what direction system we have taken arbitrarily. So when we take this, for example, you have d by dr of gm over r squared, gm over r, minus gm over r, let's call it minus 1. So when you differentiate this, this becomes minus 1 comes down, so minus 1 times by minus gm, and the power on the r becomes minus 2. So this becomes just simply gm over r squared. If you notice, this is the form for gravitational field strength. The magnitudes are matching. However, this is not entirely, one thing is missing over here. And what is missing over here is the direction component. The direction component is very important. So the direction component is that the gravitational force points inwards as we move away, as a mass moves away, as like a test mass moves away. Okay, this also means that the R is positive, moving away from the mass, like we said that. Furthermore, we also described this in the gravitational potential also, that if R is moving, like R is positive, away from the source mass, this would mean that the work done against gravity is negative towards the source mass like if the object is moved towards the source mass and positive against gravity is positive. So conclusion is that the direction over here matters quite a lot. That when we get the d phi over dr, we are getting the gm over r squared, but the phi that we calculated was the gravitational force, like in the direction of that force. But r is positive away from the source mass, so we will apply a negative sign, and this is the gravitational field. You can apply the strength over here also, this would make no difference. Oh, sorry, no. Strength. So, in short, the gravitational field strength is negative gradient of potential. Okay, so gravitational field or field strength is negative gradient of the potential graph. Another related concept, like what it simply means, is that the gravitational field, in fact, or force, acts in the direction of decreasing potential. And another thing, since it says negative gradient of potential, whether it's negative, positive, gradient of potential, that means steeper the gradient of potential, stronger the field would be. Okay. Now, let's take two scenarios from point mass, then we will see point masses, and then we will see between the planets also. So, we'll just look one small step from that. So, let's say for a simple point mass. So, let's compare the graph of potential and the field between a point mass. For a point mass, so gravitational field and potential graph for a point mass. and this will reinforce the graphs that we have already done. So let's say you have this thing, and I'll make them on the same axes just to reduce the space a little bit. So let's say, for example, the blue one is phi and the red one would be gravitational field or field strength, and this is just same as R as before. So potential, we saw that this is going to be like this. Now at infinity it will become, the gradient would become 0, but before this you see it is gradient, the gradient is decreasing. The gradient is still positive but decreasing. So gradient is positive but decreasing. So the negative of the gradient would be field. This would mean that, actually no, wait, let's make it on a different axis. Actually, no, sorry, we can make it. This would mean that the field is also in this direction. Okay, so negative of positive gradient is negative value, right? So basically this is your negative gm over r squared, which is the gravitational field. And this actually reinforces the idea that, for example, if this is your point mass, field is actually in this direction. Field actually points this way. So it has to be negative. The field direction being negative makes sense because the force is opposite to the direction of positive displacement. So force is opposite, direction of force, is opposite to that of positive displacement. So that's why it's supposed to be negative. Okay. Now, let's see what happens when you have point masses. Now we will describe, now we will make two different graphs for that, and we will describe the formulae for that also. So gravitational potential between two point masses. So when you have 2 point masses, let's say this is m1, this is m2, the potential between them is the sum of potential. So sum of potential is going to be the potential due to m1 plus the m2, the net potential basically. So this would be a minus gm over r, r being the distance, let's say, from m1, and let's say the d is the distance between them. R and plus minus gm2 from d minus r. So as you can see, the net quantity is still negative. So if we draw the graphs, so for example, let's simplify this, that m1 is equal to m2. So if we draw the graph for them, this is your phi, and this is your r. Let's say this is your d, the difference between them. So this is going, if they are same mass, like the identical masses, so it's going to go like sort of, no sorry, let's make a dotted line over here, somewhat like this, almost identical over here. Okay, now let's try to explain the shape and try to understand what the field would look like. So the direction, the gradient is positive over here. So positive gradient means negative field direction. Gradient becomes 0. So 0 gradient means 0 field strength, and the direction of the gradient is again negative. This would mean the direction is positive field direction. Okay, now this would mean that the field direction is this way, it's 0, and in this case it's in this direction. So if you recall the gravitational field graph between 2 point masses, let me show you. We can actually make a graph over here quickly. This is your R, this is your G. So the field direction would be, let's make it this way. So this would be right over here, and D is right over here. Let's say, for example, over here, let's say this is your D, right? So your field direction would be also, let's make it this way. So it's negative before that and positive after this point. So this is your field diagram, and this is exactly what we saw in the previous video also. Now notice the gradient of this is not 0, just the value of this is 0, because at this point the force direction on both the forces direction, they are balanced. The net force is 0. And as what we saw over here, positive gradient means negative field. This just means that there is going to be, like the field, the net force is in this direction. And beyond that, this would be in this direction. But what if one of the masses is heavier? For example, you have Earth and the Moon. Comparison between potential and field graph. So potential and field between, let's say, Earth and the Moon. That means M1 is significantly greater than M2. So in this case, when we have the potential formula over here, the net potential Gm1 over R plus minus Gm2 over D minus R. So closer to R, that, like for example, closer to M1, this component will be very heavy. Okay, this would actually be very heavy. So let's see how the potential graph would look like. So if we draw the graph, so potential graph would be it would be like this, from surface to surface. So for example, if this is the radius of planet Earth, let's say this is the planet radius of the this is the radius of planet Moon, and this is where your D is. So this is your radius of the planet Moon. So obviously this would mean that at the surface there is a defined value. That means also that if we go closer to the center of the point mass or closer to the point mass, the value will be different. The features of the graph are the same as before. Field direction, the gradient direction positive means field is towards the Earth. Field becomes temporarily zero, where potential dV over dr becomes zero. This means that the G this is constant, my bad, why am I saying it? The G is zero. And field direction becomes positive as the gradient has become negative. So if we draw the graph between them, okay, let's make this is your D, this is the point of zero gravity. So this would mean that the field direction is actually coming from this point and a very small magnitude over here. But at the surface or at the radius, this will be a very high negative value, and at the surface of the Moon, this would be a very, over here, my bad, and over here. So let's make it this way. So normally we just need it up till the surface, so we can make it like this. So let's clean it up a little bit. So yeah, so sort of like this. We don't need to go up till the D over here. So this is your, let's say, D. Okay. Furthermore, the values of potential and the field at the surfaces are not just Gm over R, they are influenced by the other mass also. So you have to remember this thing. The net potential or net field due to the two masses at the surface of one planet is going to be different from if it were just one planet. Alright, so this is our field graph. Alright, now moving on to the gravitational potential energy, which is a related quantity to potential. So if potential is work done per unit mass, gravitational potential energy is just the work done. So the definition is almost identical. The work done by gravitational attraction or gravitational force to bring a small test mass from infinity to a point closer in the field. So EP as before is, notice that we have just dropped it per unit mass. So if it was work done per 1 unit mass, like 1 kg, it is potential. And if it is just simply any mass, this is going to be EP. So this is basically M5. Okay. Now we can definitely relate just simple work done with gravitational potential energy. So change in gravitational potential energy requires work. So change in gravitational potential energy requires work done. Okay. Further clarification: to increase the gravitational potential energy, work is done against the field. You can say positive work done is against the field. Work is done against the field. And to decrease potential, I'm going to write it as EP. You can say positive work done is against the field, or negative work done is against, you can say the positive work done is done by the field. So positive work is done by the field. Alternatively, if positive work is done against the field, you could say negative work by the field. Similarly, positive work done by the field. This would mean that negative work against the field. That means this is going to reduce the gravitational potential energy. Or you could say that this would decrease energy. This would release energy also. This means this could release energy, and this requires energy. Okay. Now let's see what escape speed means. Or how to figure this out. So simply put, it is the speed with which a mass needs to be launched from the surface of a planet to escape the gravitational field of the planet. So let's figure this out. So let's say, for example, there is a rocket over here and it needs to go from the surface to infinity. We know the gravitational potential energy at this point. So from R, like the radius of the planet, the gravitational potential energy at this point at R, so the GPE at R is equal to minus GMM over R. So there is this mass M over here, and this is the capital mass, right? This represents the work done from infinity to that point R. This means that if we need to do work done, if we need to do work against the field, it would be the same magnitude but opposite in direction. So work done against field, gravitational field, would be from R to infinity would be GMM over R. Okay, so if this is the work done, this means that this is the minimum work that is required. Okay, so this is the minimum work done that is required. So since we know that work done results in change in kinetic energy, or delta EK. So basically this means that the EK that we require, initial EK that we require, is at least greater than this value. So your half mv squared needs to be greater than this value. So when we simplify a little bit, our velocity, launch velocity, needs to be greater than 2 gm over r, and when you square root, 2 gm over r square root. This means that the velocity should be at least this value. And notice that it doesn't depend on the mass of the launching body. It's related to the mass of the planet and the radius of the planet. So as you can see, escape speed depends on mass and radius of the planet. And is independent of the mass of object being launched. Alright. Now, this is a scenario where an object wants to go, an object is required to go from the surface of the planet to infinity. But what if the object is orbiting? So the second part of the satellites over here, energy of the satellites. Energy of satellites. So we briefly saw the system over in the first video. So when you have, for example, a central body and there is, let's say, an orbiting body, let's say this thing. This is capital mass, this is m, and the radius and the distance between the orbital radius is, let's say, r. So we remember the formula over here, since we are assuming that this is a circular orbit. The gm/r squared is equal to the centripetal force mv squared over r. So cancelling out the m and m, r and r is actually equal to v squared gm over r. Now see the distinction between this thing. This is different. So your v squared greater than 2gm over r, this is the escape speed from surface to infinity. But this is the orbital speed or speed for an orbiting body. So when you do this, this becomes gm over r. This is the speed that is required for an orbiting body or satellite. This means that we can also figure out the kinetic energy, which is half mv squared. So this becomes half m gm, so gmm over r. And we are already familiar with the potential energy in between the two. This is going to be minus gmm over r. So if we want to find out the total mechanical energy, which again remains constant, or total energy for that matter, is going to be equal to sum of both of these, so half gmm over r plus minus gmm over r. So notice gmm over r is common, so total energy comes out to be minus 1 over 2 gmm over r. So I think we can draw the graph for energy also now. This is very easy. So total energy and gravitational potential energy are both negative, but different. This is, let's say, the gravitational potential energy. Total energy would be smaller because it's half that, so let's call it just simply E. And kinetic energy was half of gmm over r. So again, it will have a similar value to, or a similar structure to this thing, E, but positive sign. So this is your energy in joules, and this is your distance, r. Now, how do we interpret this? So interpretation for this. Simple ways to interpret this. Okay. Now, we know that the kinetic energy, the change in kinetic energy is opposite to the change in potential energy. So for example, if we go from over here to over here, so for example from this point to this point, so we can see this over here, let's change the color over here, that if we move from a lower radius, let's say r1 to r2, the kinetic energy is reducing, but potential energy on the other hand is increasing. Okay, so to increase the orbit radius and increase in gravitational potential energy is required, which results in a decrease in kinetic energy. So as we go further away, the orbiting body will have lesser and lesser kinetic energy, lesser and lesser speed. Similarly, to decrease the orbital radius, gravitational potential energy decreases. Come on. Increasing the kinetic energy and the orbital speed of the satellite. That means if the satellite moves to a lower orbit, the kinetic energy and the orbital speed of that object will increase. And we already remember the rule that the time period is proportional to r cubed. So if the radius is increased, this means that the time period increases. And in this case, time period of the orbit decreases. And that's about it for this topic. If you have any confusions, doubts, or questions, feel free to reach out in the comments. In the next video, we will do some questions from paper 4 from past papers. Until the next video, take care. Bye-bye.